The universe is built by hidden forces you cannot see. Carl Sagan once reflected that we are made of star stuff, a beautiful reminder that the cosmos is not just around us, but a part of us. This journey explores 20 of these invisible architects, from the quantum foam bubbling at reality's foundations to the dark energy pushing the cosmos apart. By the end, you will understand the secret blueprint of everything, the hidden framework guiding the life of galaxies and the path of atoms. We will uncover what dark matter truly holds together and what immense energy launched the entire universe into being. What single cosmic mystery has always captivated your imagination? That first cosmic blueprint was written in the language of quantum uncertainty. In the earliest instance of the universe, what we perceive as empty space was far from empty. It was a turbulent sea, a frothing ocean of potential where particles and energy flickered into and out of existence in a frantic dance dictated by the uncertainty principle. This principle tells us that on the smallest scales, there is a fundamental limit to what we can know. We cannot precisely know both the position and the energy of a particle at the same time. This inherent fuzziness of reality means that even in a perfect vacuum, there is a constant, low-level hum of activity. These are quantum fluctuations. In the first fleeting fractions of a second after the Big Bang, during a period of hyper-accelerated expansion we call inflation, these tiny, subatomic ripples were caught and stretched. They were magnified from the quantum world to cosmic proportions, imprinted onto the fabric of spacetime itself. These imperfections became the seeds for everything we see today. As the physicist Stephen Hawking observed, the universe does not allow perfection. It was these very flaws, these minute variations in density, that gravity would later seize upon. They became the gravitational anchors around which all cosmic structure eventually coalesced, from the first stars and galaxies to the vast clusters and superclusters we observe now. We can still see the echo of these primordial ripples today. Satellites like the Planck Observatory have mapped the faint afterglow of the Big Bang, the cosmic microwave background. The subtle temperature variations in this ancient light are a direct snapshot of those initial quantum seeds, a baby picture of the universe showing the faint blueprint of its future. How might this understanding reshape our theories of cosmic origins? It forges an unbreakable link between the bizarre rules that govern the smallest particles and the grand architecture of the cosmos. The microscopic directly birthed the macroscopic, yet for these seeds to grow into a universe, they needed a sculptor, a force to pull them together from the void. This leads us to the second hidden force, the most dominant attractive power in the cosmos, gravity. Yet gravity's grand design holds a secret counterforce. As the universe expands, it does not slow under its own weight as once expected, but instead accelerates, racing outward faster with every passing moment. This astonishing discovery, which earned a Nobel Prize, points to a mysterious repulsive influence known as dark energy. It is as if the vacuum of space itself contains a hidden presence, a gentle pressure that encourages cosmic growth. Nobel laureate Saul Perlmutter called this the most profound mystery in all of physics, an unseen element that makes up the overwhelming majority of the universe's energy content. One leading idea models dark energy as a cosmological constant, a uniform energy density woven into the very fabric of spacetime. Other theories suggest it could be a dynamic field, known as quintessence, that changes over time. We see its effects etched across the cosmos. Observations of distant stellar explosions, called supernova, first revealed this steady acceleration. Further evidence comes from the subtle imprint of sound waves preserved in the distribution of galaxies, and from the way light loses energy as it travels through growing cosmic structures. This accelerating expansion paints a startling picture of the far future. Galaxies will be carried ever farther apart, their light eventually fading from view. The universe may be destined for a long, cool, and distant era, a quiet transition sometimes called the Big Freeze. What does this mean for the ultimate fate of everything we see? It suggests a cosmos where the very space between worlds becomes the dominant player. Yet, for all its power to encourage separation on the grandest scales, another hidden force works in the opposite direction, binding the largest structures in the universe together against this cosmic tide. This gravitational scaffolding, dark matter, forms the cosmic skeleton upon which everything visible is draped. Vera Rubin's pioneering work revealed a profound truth, that what you see in a galaxy is not what you get. Her observations of spiral galaxies showed their outer stars whipping around at speeds that should send them flying off into the void. They did not. Something invisible, a vast halo of unseen matter, was holding them in its gravitational embrace. This mysterious substance, which we call dark matter, does not interact with light at all. It neither emits, absorbs, nor reflects it. We cannot see it, but we can feel its pull, a ghostly presence that comprises over 1/4 of the entire universe. Without this hidden mass, galaxies would simply fly apart. Its gravity acts as the essential glue, not only binding individual galaxies, but also weaving the largest structures in the cosmos. The great cosmic web, with its glittering filaments of galaxies and vast, empty voids, is a direct imprint of dark matter's underlying architecture. The visible stars and galaxies are merely the decorative lights on this immense, invisible framework. The hunt to identify what dark matter actually is remains one of science's greatest quests. Candidates range from weakly interacting massive particles to theoretical particles called actions. While we have not yet directly detected one, the indirect evidence is overwhelming. We see its signature in the way massive galaxy clusters bend light from objects behind them, an effect called gravitational lensing. We see its necessary imprint in the precise patterns of the ancient cosmic microwave background. Perhaps the most striking proof comes from colliding galaxy clusters, like the Bullet cluster. In such encounters, the clouds of visible gas slow down as they interact, but the dark matter, which does not interact, passes right through. Observations show that the bulk of the mass, mapped by its gravitational lensing effect, is clearly separated from the visible matter. This confirms dark matter is not just hidden, ordinary stuff. It is something entirely different, the universe's most dominant yet elusive building block. How do these unseen halos shape the environments where stars and planets are born? They create the deep gravitational wells that draw in the gas to form galaxies in the first place, setting the stage for every solar system that emerges. This hidden architecture guides cosmic evolution from the background, a silent partner to gravity. But on smaller scales within the atoms themselves, another force takes command, one so powerful it can overcome gravity's pull and forge the very elements of life. Deep within the heart of every atom, a quiet tension unfolds. Protons, all positively charged, should push each other away, pulling every atomic nucleus apart instantly. Yet they do not. They are held together by the most powerful known force in the universe, the strong nuclear force. It is a binding energy of almost unimaginable strength, the ultimate cosmic glue that makes matter possible. This force works on an incredibly small scale, over distances 1,000,000 times smaller than the width of a human hair. Here, in the realm of quantum chromodynamics, the fundamental particles known as quarks are bound together by the constant exchange of force-carrying particles called gluons. The name is fitting, as they truly are the glue that holds the fabric of matter together. Without this immense force, the universe would be a quiet sea of solitary hydrogen atoms, a thin and featureless gas with no complexity, no planets, and certainly no life. It is the strong force that forges the elements of existence. In the cores of stars, including our own sun, it enables the wonder of nuclear fusion. As the physicist Richard Feynman noted, the sun's energy comes from nuclear reactions. The strong force is what makes those reactions possible, helping hydrogen nuclei overcome their mutual electromagnetic repulsion and fuse into helium, releasing the starlight that illuminates the cosmos. This stellar alchemy continues, building heavier elements in the fiery hearts of massive stars. And when such a star reaches the end of its life in a supernova event, it is the sudden shift and then powerful reassertion of the strong force that guides the dramatic collapse and forceful rebound, scattering newly formed heavy elements like carbon, oxygen, and iron across interstellar space. Every atom of gold in a piece of jewelry, every particle of iron in your blood, was created in such a stellar forge, all made possible by this hidden, binding power. How does this force ensure the stability of the matter that makes up our very beings? It represents a perfect, delicate balance, a fundamental constant of nature tuned with remarkable precision. But for all its immense strength, the strong force is confined to the infinitesimal world of the atomic nucleus. Another, far more subtle nuclear force also operates in this subatomic realm, one whose gentle touch is no less essential to the story of our existence. While the strong force binds, another power works to transform. Deep within an atom, a neutron can shift its nature, becoming a proton in a quiet act of radioactive change. This fundamental shift is guided by the weak nuclear force, the subtle architect of particle transformation. It is the only force that can alter one type of quark into another, a process essential for the nuclear reactions that power the stars. Nobel laureate Steven Weinberg emphasized that the weak force is crucial for understanding these deep particle changes. This force is carried by incredibly massive particles known as W and Z bosons, and their immense mass is the reason the weak force operates over such an incredibly short distance, confined to the tiny realm of the atomic nucleus. It possesses a unique and mysterious property, a violation of parity symmetry. This means the weak force can distinguish between a particle spinning to the left and one spinning to the right, introducing a fundamental handedness to the universe at the most basic level. Its most familiar role is in beta decay, where it enables a neutron to turn into a proton, releasing an electron and an antineutrino. But its true cosmic importance is revealed in the heart of our Sun. There, the weak force begins the proton-proton chain, the first slow, careful step in the fusion process that converts hydrogen into helium and bathes our solar system in light. Without this initial transformation, stars could not shine. In the intense final moments of a massive star, a supernova, the weak force takes center stage once more. As the stellar core collapses, it is the interactions guided by this force that release a flood of neutrinos. This neutrino surge helps drive the shockwave that disperses the star, scattering newly created heavy elements like gold and uranium across the galaxy. How does this force influence the abundance of elements in the cosmos? It is the critical gatekeeper, controlling the rate at which protons can be added to nuclei, thereby shaping the entire periodic table that we find spread throughout the universe. This subtle interplay between nuclear forces forges the very stuff of worlds, but once these elements are formed, another, more familiar force takes command, one that dictates how they interact with the most fundamental cosmic messenger, light itself. A universe without light would be a story told in silence. From the fiery heart of a star to the delicate glow of a firefly, the force of electromagnetism is the artist behind all illumination. It is the master of interaction between charged particles, a long-range force that dictates how atoms bond into molecules and how energy travels across the vast emptiness of space. The physicist James Clerk Maxwell captured its essence in a set of beautifully elegant equations, unifying electricity and magnetism into a single, coherent framework. His work revealed that light itself is an electromagnetic wave, a self-propagating dance of electric and magnetic fields traveling through the void. This force is carried by the photon, a massless particle of pure energy that acts as the universe's primary messenger. Without electromagnetism, atoms could not hold their structure, chemistry would not exist, and the cosmos would be utterly dark and unrecognizable. Its influence extends from the smallest scale to the grandest. Within a star, electromagnetic pressure helps counteract the immense crush of gravity, creating a stable environment for nuclear fusion to occur. The light that then streams outward is electromagnetic energy, carrying information across billions of light years to our telescopes. We do not just see the universe in visible light, we observe it through the full spectrum of this force, from the long, gentle waves of radio astronomy that map cold gas clouds to the powerful, penetrating gamma rays that signal the most violent explosions. Look at the center of our own Milky Way, and you will find it illuminated by synchrotron radiation, a brilliant light show created by electrons spiraling at nearly the speed of light through powerful magnetic fields. This same fundamental force powers our modern world, from the electricity in our homes to the magnetic fields that guide our compasses. How does this pervasive force facilitate the exchange of energy that allows us to see and understand the cosmos? It is the fundamental channel for information, the means by which every star, every galaxy, and every cosmic event announces its presence to the rest of the universe. Yet for all its power to carry signals across space, another, more subtle kind of message is being sent, not through the electromagnetic spectrum, but through the very fabric of reality itself, a disturbance that travels as a ripple in spacetime. That gentle hum of electromagnetism carries a story, but sometimes the universe sends its most dramatic messages not through light, but through silent shudders in the fabric of reality. Two black holes, each containing the mass of dozens of suns, spiral toward each other in a final, frantic dance. As they merge into a single, more massive object, they unleash a storm of energy, sending ripples racing outward at the speed of light. These are gravitational waves, distortions in spacetime itself, exactly as Albert Einstein predicted a century ago. They are not waves in space, but waves of space, stretching and compressing everything in their path, including the distance between atoms. For decades, this was just a theoretical prediction, but in 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection. The signal matched the precise waveform of two black holes interacting over 1 billion light-years away. As physicist Kip Thorne, a pioneer of the research, noted, gravitational waves open a new window on the universe. This was not seeing the cosmos, it was listening to it, hearing the vibrations of spacetime. These waves are generated by some of the most energetic events imaginable, from the mergers of neutron stars to the core collapse of supernova. Detecting them is a feat of incredible precision. Facilities like LIGO use laser beams traveling down 4-kilometer-long arms. A passing gravitational wave minutely changes the length of one arm relative to the other, a shift thousands of times smaller than a proton. By measuring this tiny wobble, we can reconstruct the cosmic event that caused it. A landmark moment occurred in 2017, when observatories detected both gravitational waves and a flash of light from the same source, two neutron stars merging. This multi-messenger astronomy gave us a complete picture of the event, confirming that such interactions are cosmic forges for heavy elements like gold and platinum. How do these waves help us test general relativity in the most extreme environments? They allow us to probe the nature of gravity near black holes, verifying that their behavior matches Einstein's predictions under conditions of immense strain. Every ripple we capture is a direct signal from the warped geometry of spacetime, a dynamic perspective on the forces that shape the cosmos. This new sense is tuning us into the universe's most powerful rhythms, vibrations that began with the very first moments of existence in the expansive field that set everything in motion. The silent tremors of gravitational waves carry us back to the very beginning, to a moment of unimaginable transformation. In the first sliver of a second after the Big Bang, the universe experienced a growth spurt of epic proportions, expanding faster than the speed of light itself. This was the era of inflation, driven by a powerful and hidden field that smoothed the cosmos into the universe we recognize today. Physicist Alan Guth, who first proposed this idea, famously called the universe the ultimate free lunch, a reference to the immense cosmic structure that grew from almost nothing. This inflationary field, a kind of high-energy scaffold woven into space, pushed everything apart with incredible force. It solved two profound puzzles in one stroke. The horizon problem asks why the universe looks so uniform in all directions, even though there was not enough time for light or heat to travel across it to even out the temperature. Inflation stretched a tiny, homogeneous patch to become our entire observable cosmos. The flatness problem asks why the geometry of our universe is so perfectly balanced, neither positively nor negatively curved. Inflation stretched space so dramatically that any initial curvature was flattened out, like smoothing the wrinkles from a sheet. The evidence for this early period of rapid expansion is written in the oldest light we can see. The cosmic microwave background shows a remarkably uniform temperature across the sky, just as inflation predicts. More importantly, the subtle variations in that temperature, the tiny hot and cold spots, match the spectrum of primordial density variations that inflation would have generated from quantum fluctuations. Without this brief but powerful period of expansion, the universe might have collapsed back on itself almost immediately, or become far too lumpy for galaxies to ever form. The implications stretch even further. Some models suggest inflation is eternal, continuously giving rise to new pocket universes in an endless multiverse, each with its own unique laws of physics. How does this reshape our view of cosmic origins? It suggests our entire reality may be just one bubble in a vast cosmic foam, all born from the relentless energy of an inflationary field. This early beginning connects directly to the quiet energy that now fills the vacuum of space, a persistent presence that continues to guide the cosmos. That same vacuum of space, seemingly an absolute void, is in fact a vibrant sea of energy. The emptiest regions of the universe are not empty at all, but filled with a constant, low-level hum of activity known as vacuum energy. This is the energy of the quantum field itself, present even at absolute zero temperature, a restless sea where particle and antiparticle pairs flicker into existence for fleeting moments before returning to the background state. This is the zero-point energy of the cosmos, a foundational concept in quantum field theory that fundamentally reshapes our idea of nothingness. The physicist John Wheeler poetically described the nature of spacetime at its smallest conceivable scale as quantum foam, a turbulent, churning landscape where the very concepts of space and time break down. One of the most striking demonstrations of this hidden energy is the Casimir effect. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they will experience a faint but measurable force pulling them together. This happens because the space between the plates restricts the kinds of quantum fluctuations that can occur there, while the fluctuations outside the plates remain unrestricted. The greater pressure from the outside pushes the plates together, a physical proof that the vacuum is alive with transient forces. This is not just a theoretical curiosity. It has been confirmed in laboratory experiments and has real-world consequences, especially in the realm of nanotechnology, where it can influence the operation of incredibly small mechanical devices. The implications of vacuum energy stretch to the very edges of the cosmos, as it is intimately linked to the concept of the cosmological constant and the mysterious dark energy that drives the universe's accelerating expansion. Yet here we encounter one of the most profound puzzles in all of physics. When theorists attempt to calculate the expected density of this vacuum energy based on quantum principles, the result is a number staggeringly larger than what we observe from cosmic expansion, differing by over 120 orders of magnitude. This colossal mismatch, known as the cosmological constant problem, suggests a deep flaw in our understanding, or a remarkable cancellation of forces we do not yet comprehend. How does this invisible background energy influence the formation and evolution of cosmic structures? It is a subtle pressure woven into the fabric of reality, a persistent whisper that may guide the very architecture of galaxies. This hidden energy of the vacuum works in concert with another invisible force that shapes galactic disks and channels the flow of interstellar gas, the cosmic magnetic field. These vast magnetic fields are the silent architects of galactic structure, weaving invisible lines of force through the emptiness between stars. While we cannot see them directly, their presence is felt everywhere, sculpting the flow of interstellar gas and guiding the birth of new solar systems. The astrophysicist Hans Alfvén, a Nobel laureate, described this relationship perfectly, noting that the magnetic field is the skeleton of the plasma. This hidden framework gives shape and direction to the turbulent, ionized gases that fill galactic space. The origins of these cosmic fields are thought to lie in faint, primordial seeds from the early universe. Over billions of years, the churning motions of plasma, driven by the rotation of galaxies and the turbulence of supernova explosions, have amplified these weak seeds into the powerful, organized fields we detect today. We observe their signature through the polarization of starlight, which becomes subtly aligned as it passes through magnetized dust, and through the brilliant synchrotron radiation emitted by electrons spiraling at nearly light speed along these invisible pathways. Within our own Milky Way, this magnetic architecture helps to maintain the majestic spiral arms and contains the expanding remnants of ancient stellar transitions, shaping them into intricate, bubble-like structures. These fields also play a crucial role in the nurseries of star formation. As a massive cloud of molecular gas begins to collapse under its own gravity, the embedded magnetic field provides a form of support, resisting the collapse and slowing the process. This magnetic braking allows the cloud to fragment more efficiently, ultimately determining the sizes and numbers of the stars that will be born. How do these fields contribute to the stability and evolution of cosmic structures? They act as a regulating force, a cosmic traffic director for interstellar material and high-energy particles. Even the most energetic cosmic rays, protons and atomic nuclei traveling at nearly the speed of light, are deflected and channeled by these galactic magnetic fields, their paths scrambled into a random walk across the galaxy. This pervasive, structuring influence reaches back to the universe's earliest moments, connected to another relic from a time when the cosmos was a seething plasma of fundamental particles. While magnetic fields sculpt the visible cosmos, a far more elusive ocean of particles flows through it, a ghostly echo of creation itself. Just 1 second after the Big Bang, a vast sea of neutrinos decoupled from ordinary matter and began streaming freely across the expanding universe. This cosmic neutrino background is a relic as fundamental as the cosmic microwave background, yet infinitely harder to perceive. Its existence was first hinted at by Wolfgang Pauli, who, upon postulating the neutrino, famously lamented that he had done a terrible thing by conceiving a particle that could not be detected. He was nearly right. These particles are so ethereal that trillions pass through your body every second without a single interaction. They possess tiny but non-zero masses and interact only through the weak nuclear force and gravity, making them the universe's most perfect ghosts. Yet their collective gravitational influence is profound. In the early universe, neutrinos made up a significant fraction of the energy density. Their tendency to fly freely at nearly the speed of light, a behavior known as free streaming, meant they could smooth out the primordial lumpiness of matter. This gentle washing out effect subtly slowed the growth of the very first gravitational seeds, leaving a lasting imprint on how galaxies cluster together on the largest scales. We cannot detect this background directly with current technology, but we can see its shadow. Precision data from the Planck satellite, which mapped the cosmic microwave background, reveals subtle patterns that constrain the number of neutrino species and their total mass. The observed distribution of galaxies in massive surveys also bears the signature of this damping effect, showing us how these ghostly particles help to sculpt the cosmic web. How do these nearly massless travelers influence the grand architecture we see today? Their free streaming creates a fundamental shift in the timing and scale of structure formation, a subtle pressure that guides where great walls of galaxies can form and where vast empty voids must remain. This gentle sculpting force is intertwined with another relic of the early universe, a frozen sound wave imprinted on the distribution of matter known as baryonic acoustic oscillations. That faint echo from the neutrino background is not the only frozen rhythm from the early cosmos. There is another, more distinct pattern etched into the universe, a fossilized sound wave that serves as one of our most precise cosmic measuring tapes. In the first few 100,000 years after the Big Bang, the universe was a searing, opaque plasma, a thick soup of atomic nuclei, electrons, and photons. In this dense medium, gravity would pull matter inward, trying to collapse it, while the immense radiation pressure from the trapped photons would push it outward. This tug-of-war created vast, spherical pressure waves that rippled through the primordial soup, much like sound waves moving through air. These are the baryonic acoustic oscillations. They traveled outwards at over half the speed of light until a pivotal moment, when the universe cooled enough for atoms to form and photons to decouple, flying free as the cosmic microwave background. At that instant, the waves froze in place, their progress halted. The result was a subtle, repeating pattern in the distribution of matter, a preferred scale where galaxies were slightly more likely to form. Cosmologist David Schlegel aptly described this pattern as a standard ruler for the cosmos. That ruler has a fixed length, a characteristic size of about 500 million light-years, imprinted across the entire sky. Modern astronomical surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument use this ruler with incredible precision. By measuring the apparent size of this baryonic acoustic oscillation pattern at different cosmic distances, we can track how the scale of the universe has stretched over billions of years. It is as if we found a fossilized ripple in space-time and can measure how much it has been expanded over the eons. these measurements have provided some of the strongest independent confirmations that the expansion of the universe is accelerating, driven by dark energy. They constrain the geometry of the cosmos, pointing toward a flat universe and helping us measure the exact proportions of dark matter and dark energy. How does this oscillatory pattern connect to the scalar fields theorized to drive cosmic acceleration? The precise scale of these frozen waves is deeply tied to the physics of the primordial universe, including the behavior of the very fields that may have powered inflation and that might now manifest as dark energy. This cosmic ruler, built from the first sounds of creation, gives us a direct link to the forces that continue to shape our cosmic destiny, guiding us toward an even more fundamental layer of reality, where the rules of physics themselves may have been written. The concept of a static vacuum energy is a profound puzzle, but what if the force driving cosmic acceleration is not constant at all? Imagine a dynamic, invisible fluid suffusing all of space, a field whose energy and pressure evolve with the age of the universe. This is the theoretical concept of quintessence, a scalar field that represents a compelling alternative to the cosmological constant. Physicist Sean Carroll has highlighted its potential, noting that quintessence could solve the coincidence problem of why dark energy dominates now. Why, after billions of years of matter-dominated expansion, has this repulsive force only recently taken control of the cosmic destiny? A static vacuum energy would have always been a fixed fraction of the total, making its current dominance seem like a strange accident in time. A dynamic quintessence field, however, could have lain dormant for eons, its energy density fading slowly while matter diluted more rapidly, only to emerge as the dominant component in the recent cosmic era. This field would possess a negative pressure, a kind of cosmic tension that causes it to gravitationally repel itself and everything else, driving the observed acceleration. Its key signature would be a value for its equation of state, a parameter describing the relationship between its pressure and density that differs from the simple constant predicted by a cosmological constant. We hunt for this signature in the detailed data from distant supernova and the subtle patterns in the cosmic microwave background, searching for any hint that the strength of dark energy has changed over billions of years. In theoretical models, this is often visualized as a ball rolling slowly down a gentle potential hill, its changing position representing the evolving energy density of the field. Some models even suggest this field could interact with dark matter, creating a subtle link between the invisible cosmic scaffolding and the force shaping its expansion. Such an interaction would leave an imprint on the rate at which galaxies and clusters form, offering another observational path to its discovery. How could such an evolving force alter our cosmic future? It opens dramatic possibilities, from an eternal acceleration to a future where the field decays, causing the expansion to slow once more, or even a reversal leading to a big crunch. This idea of dynamic fields changing the fate of everything leads us to consider other, more exotic relics from the early universe, frozen features in the fabric of spacetime itself. The fabric of reality itself may contain frozen cracks, relics of a time when the universe underwent a profound and sudden change. In its earliest, hottest moments, the cosmos was likely unified under a single, symmetric force. As it expanded and cooled, this symmetry broke, much like water freezing into ice. And just as ice forms cracks and flaws as it freezes, the structure of spacetime itself may have crystallized with imperfections. These are topological defects, cosmic imprints from the dynamic beginnings of physics as we know it. One of the most intriguing possibilities is the cosmic string, a theoretical filament of pure energy thinner than a proton but stretching across the universe, with the mass of a mountain range packed into every inch. As physicist Tom Kibble described, these relics could have seeded galaxy formation, their immense gravitational pull acting as early anchors for matter. A network of such strings vibrating across the cosmos would be a source of continuous gravitational waves, a faint background hum from the universe's first moments. We hunt for their subtle signatures. A cosmic string would warp the space around it so profoundly that it could split the image of a distant quasar into two identical copies. Its passage would create a sharp, step-like discontinuity in the cosmic microwave background, a line in the sky where the temperature of the ancient light suddenly shifts. While precise observations from the Planck satellite have so far found no evidence for such features, placing strict limits on their possible density, the search continues. How do these exotic structures test theories beyond the standard model? Their existence is a direct prediction of grand unified theories that attempt to merge the fundamental forces. Finding one would be a window into energy scales 1 trillion times beyond what any particle collider can reach, confirming that the universe underwent these dramatic phase transitions. The concept of frozen, information-rich structures in spacetime leads to a truly radical idea that our three-dimensional reality might be a projection from a two-dimensional surface, a cosmic hologram. That radical idea of cosmic cracks leads to an even more profound possibility that our universe of 3 dimensions is a grand illusion, a projection from a 2-dimensional surface. This is the holographic principle, a concept that fundamentally reshapes our understanding of reality's very fabric, proposed by physicists Gerard T. Hooft and Leonard Susskind. It suggests that all the information describing everything within a volume of space, every star, every planet, and every one of us, is actually encoded on its outer boundary like a cosmic DVD. As Susskind himself stated, the holographic principle is a radical new way to think about space. It tells us that the maximum amount of information a region can contain is not proportional to its volume but to its surface area. This turns our everyday intuition inside out, implying that the rich, three-dimensional world we experience might be a holographic projection from a vast, distant, two-dimensional screen. This astonishing idea emerges from the thermodynamics of black holes. When matter crosses into a black hole, it appears to vanish from our view, but its information, according to quantum mechanics, cannot be truly erased. The holographic principle resolves this black hole information paradox by suggesting that the information of everything that crosses the boundary is not lost inside, but is instead imprinted onto the black hole's event horizon, its one-way boundary, and is eventually returned as the black hole slowly fades. This means a black hole is the most efficient information storage device in the universe, its entire interior content perfectly described by the data on its surface. How does this informational limit apply to the cosmos as a whole? Our entire observable universe has a horizon, a point beyond which light has not had time to reach us. The holographic principle suggests that the total information and the ultimate entropy of everything we can see is also finite, encoded on this cosmic boundary. This informational perspective offers a new path to unifying gravity with quantum mechanics, a central goal of string theory. It implies that gravity itself may not be a fundamental force, but an emergent phenomenon, a consequence of the way information is stored and processed on the lower dimensional surface. In cosmological models, this principle can influence our understanding of inflation and the large-scale structure of the universe, providing a different mathematical framework to describe its origins and evolution. This perspective naturally connects to ideas of fine-tuning, suggesting that the specific, information-rich laws of our universe might be one of many possible projections from a vast ensemble of simpler, two-dimensional realities. How does this informational view reshape the very definition of existence? It proposes that the cosmos is not primarily a collection of things, but a flow of information, a cosmic computation whose output is the reality we perceive. This informational foundation of everything points toward the next hidden force, the very laws and constants that seem perfectly arranged to allow for our existence. This holographic view of reality, where information defines existence, leads to a startling question. Why do the fundamental laws of physics seem perfectly arranged to allow for our presence here to ask it? This is the domain of the Anthropic Principle, a concept that stands at the crossroads of physics and philosophy. It suggests a simple yet profound observational selection effect. The universe we measure must be compatible with the conscious life that measures it. As physicist Brandon Carter noted, our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. The evidence for this fine-tuning is etched into the cosmos itself. Consider the strength of the dark energy density, the cosmological constant. If it were even slightly stronger, the universe would have blown itself apart before stars could ever form. If it were slightly weaker, everything would have collapsed back into a cosmic reversal long ago. The precise balance allows for a long, fertile era where galaxies could assemble and life could eventually emerge. The same delicate balance applies to the fundamental forces. A tiny increase in the strength of the strong nuclear force, and protons would bind so tightly that no hydrogen, the fuel of stars, would remain. A small decrease and complex atomic nuclei could never form, leaving the universe with only the simplest elements. The initial conditions of the Big Bang itself were set with an accuracy of 1 part in many trillions, a launch so precise it defies simple chance. How do we explain this astonishing precision? One compelling answer lies in the concept of a multiverse. If our universe is just one bubble in a vast cosmic foam, a single realization in an endless string landscape of possibilities, then each pocket universe can have its own unique set of physical constants and laws. We find ourselves inevitably in one of the rare bubbles where the numbers are just right for complexity and life. This is not a designed universe, but a selected one. This perspective reframes the question of purpose. We are not asking why the universe is fine-tuned for us, but rather why we find ourselves in a universe capable of supporting us. The debate over its scientific validity is intense, with some seeing it as a necessary insight and others as an untestable retreat from explanation. Yet its influence is undeniable, guiding theories of cosmic origins toward frameworks that can naturally generate such diversity. This fine-tuned reality is deeply connected to the flow of time itself, to the very arrow that gives us a past and a future, and to the role of entropy in shaping the cosmic story. The universe remembers its beginning, a state of exquisite order that set the clock of time ticking forward. This relentless drive toward increasing disorder, known as entropy, is the hidden force that gives time its irreversible direction. The physicist Arthur Eddington expressed it beautifully: entropy is time's arrow. It is the reason we remember the past but not the future, the force that ensures a dropped glass shatters but never spontaneously reassembles. In the first moments after the Big Bang, the cosmos was in a state of remarkably low entropy, a condition of smooth, uniform density that was the ultimate starting point for everything to come. This initial order was not a static perfection, but a wound-up spring, a reservoir of potential that the universe has been spending ever since. As gravity began its work, it played a paradoxical role. While the overall entropy of the universe increases, gravity can create pockets of stunning local order, like swirling galaxies and brilliant stars from the initial chaos. A uniform gas cloud has lower gravitational entropy than a cluster of stars, so the very act of structure formation, of pulling matter together, drives the increase of total entropy. We see the pristine evidence of this low entropy passed in the cosmic microwave background. Its near-uniform temperature across the sky is a snapshot of that smooth, ordered beginning. The formation of a single star is a process that dramatically increases entropy as the concentrated nuclear fuel is dispersed into light and heat that radiates out into the cold void. Even a black hole, the ultimate manifestation of gravity, carries entropy directly proportional to the area of its event horizon, a concept that lies at the heart of the holographic principle. This cosmic journey from order to disorder points toward a final, quiet state, a distant future often called the heat death, where energy is evenly distributed and no more work can be done. How does this thermodynamic force guide the universe's grand evolution? It provides the narrative direction for the entire cosmic story, from a hot, dense beginning to a cold, diffuse end. Yet at the most fundamental level, this arrow of time and the very fabric of spacetime may emerge from a deeper, more subtle phenomenon, the quantum connections that entangle particles across the cosmos. Einstein famously called it spooky action at a distance, a phrase that captures the deep unease this phenomenon once caused. Quantum entanglement links the fates of two particles, no matter how far apart they travel. Change the state of one, and its partner responds instantaneously, a connection that seems to defy the cosmic speed limit of light. This is not a mere theoretical curiosity. It has been confirmed in laboratories again and again, proving that the universe possesses a layer of reality that is deeply, fundamentally interconnected. The implications stretch far beyond the laboratory, reaching into the very nature of space and time. The revolutionary idea known as ER equals EPR proposes that two entangled particles are, in fact, connected by a microscopic wormhole, a bridge in the fabric of spacetime. This suggests that the spooky link of quantum entanglement and the geometric warping of general relativity are two sides of the same cosmic coin. The physicist Juan Maldacner's work on the AD-SCFT correspondence provides a mathematical framework for this, suggesting that the geometry of spacetime itself is woven from a vast, dense web of quantum entanglement. In this view, entanglement does not happen within space, it creates space. The smooth, continuous universe we perceive emerges from countless quantum bits sharing information, a cosmic tapestry knitted together by invisible threads of connection. This perspective offers a profound clue to one of the universe's earliest mysteries, its remarkable uniformity. The distant regions of the cosmic microwave background are so similar in temperature that they should have been in contact, yet in a conventionally expanding universe, there was never enough time for light or heat to travel between them. How did they reach this equilibrium? The answer may lie in primordial entanglement. If these vastly separated regions were quantum entangled in the first instance of the cosmos, they would have shared a common state from the beginning, explaining their matching properties without any need for conventional communication. This entanglement could be the hidden reason the universe appears so smooth and homogeneous on the largest scales. How does this quantum glue resolve the fundamental conflict between gravity and quantum mechanics? It suggests that gravity is not a fundamental force, but an emergent property, a thermodynamic consequence of the universe's underlying quantum information system. The very fabric of spacetime and the force that shapes it may be born from the collective behavior of entangled quantum data. This radical rethinking of gravity's origin opens the door to considering whether the force we experience is the complete picture, or if it requires modification under certain extreme conditions. The cosmic glue of entanglement suggests gravity emerges from a deeper layer of reality. But what if gravity itself is not what we think it is? An alternative path confronts the mysteries of dark matter and dark energy directly, proposing that our fundamental theory of gravity is simply incomplete. These are the modified gravity theories, a bold reimagining of Einstein's legacy that seeks to explain the cosmos without invisible components. Physicist Mordechai Milgrom, a leading voice in this field, stated that MUN challenges the dark matter paradigm. His theory of modified Newtonian dynamics was born from a specific puzzle: the unexpectedly flat rotation curves of galaxies. Instead of stars slowing down as they orbit farther from the galactic center, as standard gravity predicts, their speeds remain constant. The mainstream solution is a halo of dark matter providing extra gravitational pull. MUN proposes a different answer, that the laws of motion change at very low accelerations, like those experienced in the outer reaches of galaxies. It introduces a new constant of nature, a tiny acceleration threshold below which gravity behaves differently, strengthening its grip. This single adjustment successfully predicts the rotation of many spiral and dwarf galaxies with remarkable precision, all without a single particle of dark matter. The theory has evolved into more sophisticated relativistic versions, like tensor vector scalar gravity, which aim to fully incorporate the lessons of general relativity and make new predictions for phenomena like gravitational lensing. How do these ideas push the boundaries of fundamental physics? They force us to question our most basic assumptions about force and inertia. The ongoing tests are intense and precise. Wide-field galaxy surveys map the distribution of matter and the effects of gravitational lensing on a colossal scale, searching for the subtle signatures that distinguish a modified gravity universe from one filled with dark matter. The timing of signals from orbiting pulsars and the detailed observations of galactic clusters provide crucial testing grounds. For instance, while MUN excels at describing individual galaxies, it faces significant challenges in rich galaxy clusters, where the apparent mass discrepancy is far greater, often requiring some additional, unseen mass to explain the observations. Similarly, the intricate pattern of the cosmic microwave background, a key success of the standard dark matter model, is difficult for many modified gravity theories to replicate perfectly. The debate is far from settled. Each new observation, from the precise orbits of distant stars to the faint echoes of gravitational waves, sharpens the confrontation between these competing visions of reality. This struggle to redefine our most familiar force leads us directly to the final, and perhaps most persistent, hidden force in the cosmos, the enduring mystery of the cosmological constant itself. The cosmological constant stands as the final piece in our standard cosmic blueprint, a single symbol that represents the greatest mystery in modern physics. Enshrined in the lambda CDM model, this Greek letter lambda signifies a constant energy density inherent to the vacuum of space, the simplest possible explanation for the dark energy driving cosmic acceleration. It is the ultimate hidden force, a mathematical term that Albert Einstein initially introduced as a stabilizing factor to keep the universe static, later calling it his greatest blunder. Yet this very concept was revived decades later when astronomers discovered the universe was not just expanding, but its expansion was speeding up. The lambda CDM model, which pairs this constant with cold dark matter, has become the concordance model of cosmology because it fits an astonishingly wide range of data. It perfectly matches the detailed fluctuations in the cosmic microwave background. It explains the large-scale distribution of galaxies, and it accounts for the observed accelerating expansion from distant supernova. For all its success, this model presents a problem of almost unbelievable proportions. When we calculate the expected energy of the quantum vacuum using our best theories of particle physics, the result is a number that is 10 to the power of 120 times larger than the value we actually observe. This is not a small discrepancy. It is the most spectacular mismatch of a theoretical prediction in the entire history of science. As the physicist Steven Weinberg reflected, the cosmological constant is the most perplexing problem in theoretical physics. Why is the observed value of dark energy so infinitesimally small, yet not quite zero, a precise tuning that allows galaxies, stars, and life to exist? One possibility is that we are missing a fundamental piece of the puzzle, a new symmetry or a mechanism in quantum gravity that naturally cancels out the vacuum energy to nearly nothing. Another, more cosmic explanation returns us to the Anthropic Principle. In a vast multiverse, every possible value of the cosmological constant is realized somewhere. We inevitably find ourselves in one of the rare universes where the constant is small enough for structure to form. The quest to solve this puzzle drives the next generation of cosmic exploration. Missions like the Euclid satellite are now mapping the geometry of the universe with unprecedented precision, testing whether lambda has truly remained constant over billions of years or if it hints at a more dynamic field. How does this single term encapsulate the enduring frontier of cosmology? It represents a profound gap in our understanding, a silent question mark written into the fundamental equations of reality. This foundational constant completes our list of 20 hidden forces, yet their collective whisper points toward an even deeper truth, a unified symphony of cosmic architecture waiting to be heard. Even light itself carries the subtle fingerprints of dark energy's work across the ages. As ancient photons from the cosmic microwave background travel for billions of years to reach us, they do not journey through a static cosmos. They pass through vast hills and valleys of gravitational potential, the deep wells sculpted by dark matter and galaxy clusters. When a photon falls into one of these cosmic wells, it gains a tiny bit of energy, appearing slightly hotter. When it climbs out, it loses energy, appearing cooler. In a universe where matter completely dominates the expansion, these gains and losses would perfectly cancel out. But we do not live in that universe. The accelerating expansion driven by dark energy causes these large-scale gravitational potentials to weaken over time. The cosmic hills are slowly eroding, so when a photon climbs out of a potential well, it finds the walls have become a little less steep, and it does not have to expend as much energy to escape. It emerges slightly hotter than it should, carrying a tiny, residual warmth imprinted upon its journey. This is the integrated Sachs-Wolfe effect, a direct signal of the universe's changing gravitational landscape. Cosmologist Robert Crittenden described it as a direct probe of dark energy's influence. We detect this subtle signal not by looking at the cosmic microwave background alone, but by cross-correlating its temperature map with traces of the large-scale structure in the nearby universe, like the distribution of millions of galaxies. The observed correlation, this faint statistical warmth where the ancient light overlaps with modern cosmic structures, is exactly what the presence of dark energy predicts. It is an independent line of evidence, separate from supernova or baryonic acoustic oscillations, that points to the same accelerating reality. How does this effect help map the expansion history? It provides a timeline, a way to see how the gravitational potentials have been changing over the last several billion years, confirming that a repulsive force began to dominate the cosmos's evolution. This whisper from traveling light confirms that the hidden forces we have explored are not isolated actors, but interconnected threads in a single, magnificent cosmic tapestry, a story whose final chapter is still being written. Our journey through these 20 hidden architects reveals a cosmos far richer and more dynamic than meets the eye. From the quantum seeds of all structure to the subtle pull of unseen matter, from the binding power of nuclear forces to the cosmic expansion of dark energy, each layer intertwines to form the intricate architecture of reality. These forces collectively shape everything from the grand sweep of galactic superclusters down to the delicate dance of entangled particles, reminding us that the universe is a deeply interconnected and ever-evolving tapestry. This grand synthesis, this hidden blueprint, deepens our appreciation for the sheer improbability and wonder of existence. It invites a profound curiosity, a driving need to look ever deeper, as Carl Sagan once inspired, somewhere, something incredible is waiting to be known. That quest continues with powerful new tools. The James Webb Space Telescope peers into the nurseries of the first stars and galaxies, while the upcoming LISA mission will listen for the faintest ripples in spacetime from merging supermassive black holes. Each new observation, each fresh piece of data, is a potential key to unlocking the next layer of cosmic mystery. I would love to hear which of these hidden forces captured your imagination the most. Share your thoughts in the comments below, and if you enjoyed this deep dive, subscribe for more journeys into the heart of space's greatest mysteries. Thank you for joining this cosmic voyage. May your wonder for the universe and your questions about its hidden nature never fade.